Welcome to Study Loop.
So here would be the diagram of exactly what's just of the system here. We're going to point the boat downstream just so that the algebra would be a little bit less confusing. It would be a lot more complicated if we were to point this upstream. So we're going to say we're going to point it downstream, and if the answer that we get is negative, then we know that we're in the opposite direction, and then we're going to need to point it upstream. So, but for now, let's say that we're going to point the boat downstream. And again, if we get a negative answer, we know that we chose the wrong direction. However, it's much easier to get to that answer if we say that if we point the boat downstream initially. At this point, we're going to say that the velocity of the boat relative to the water is 1.60 meters per second. We're going to say that the velocity of the water relative to the shore, or the current, is going to be 0.80 meters per second. We can say that his running speed, the boy's running speed, is going to be 3.00 meters per second. Excuse me. We know the width of the river is 1,200 meters, and we know that the length traveled along the bank would be L. So L would equal length traveled along bank. And so at this point, we can say that the actual velocity vector of the boat, so we can say that the velocity of the boat relative to the shore would be equal to the velocity of the boat relative to the water plus the velocity of the water relative to the shore, or the current. So we can say that W is going to be equal to the velocity of the boat relative to the water times cosine of phi times t, and L in this case would be equal to the velocity of the boat relative to the water times sine of phi plus the velocity of the water relative to the shore times t sub w. And here we can say that L will be equal to v sub r t sub r. And so here t sub w is the time spent in the water, and then t sub r would be the time running, and t here would be time in the water. So at this point, we also know that the total time, of course, would simply be t sub r plus t sub w. So at this point, we can then use the distance relationships above to write the function. So t total would be equal to, again, t sub w plus t sub r. I think I just, we got a new workbook. This would be equal to t sub w plus L over the velocity of running. And this would equal t sub w plus velocity b sub w sine of phi plus the velocity of the water relative to the shore times t sub w divided by the velocity when the boy is running. And then we can factor out a t sub w. So t total be equal to t sub w times 1 plus, and then again, velocity of the boat relative to the water, sine of phi, plus velocity of the water relative to the shore, divided by v sub r. Close parentheses. This is going to equal, we can say, let's get a new line. This would be w over velocity of the boat relative to the water times the velocity of running times cosine of phi times v sub r plus v sub ws, water relative to the shore, plus the velocity of the boat relative to the water, sine of phi. And we can say that this is going to equal W over the velocity of the boat relative to the water times the velocity of the man running times the velocity of R plus the velocity of the water relative to the shore times secant of theta plus the velocity of the boat relative to the water tangent of phi, close parentheses. And so at this point, we can say that to find the angle corresponding to the minimum time, we can take the derivative of t with respect to phi, set this equal to 0, and then solve for the angle phi. So this would be equal to the derivative of what we just found, the derivative of this term right here. So the derivative of that would be equal to W over V BW times V over, or V sub R rather, times V sub R plus V sub WS, close parentheses, tangent of phi, secant of phi, plus the velocity of BW, secant squared of phi. And this is again going to equal 0. So then we can say that velocity of sub R plus velocity of the water relative to the shore times tangent of phi plus the velocity of the boat relative to the water times secant of phi parentheses times secant of phi. Once again, this will equal 0. And so we can say that here secant of phi can equal 0, or sine of phi would equal negative 1 times the velocity of the boat relative to the shore divided by the velocity of the man running plus the velocity of the water relative to the shore. We know that this answer is impossible, so we can eliminate that. We're going to use this. And so we can say that, we can solve rather, say that this is negative 1.60 meters per second divided by 3.00 meters per second plus 0.80 meters per second. And phi would equal arcsine of negative 0.421 equaling negative 24.9 degrees. Notice we got a negative number. So our direction, when we said that the point the boat downstream, that's not going to be right because we got a negative answer. Therefore, we're going to have 24.9 degrees. This would be upstream. So we can, to know that this is a minimum though and not a maximum, we need to graph it. I mean, we can do the second derivative test in order to see if this is truly a minimum, but that would be, I mean, we'd have to take another derivative, and that would be very cumbersome, especially algebraically. So we're going to actually graph the time in seconds versus angle degrees. And when we graph that, we can see that here, this would be the graph, and this would be, of course, right here would be our answer, being, again, 24.9 degrees. That would be our negative 24.9 degrees. That would be our true minimum. Therefore, we know that this angle would prove to be a minimum time. We're going to find the time that the man takes in getting to the final location. This can be calculated from the angle with which we just calculated. So we can say that T sub W is going to be equal to W over the velocity of the boat relative to the water times cosine of phi. We're just taking the equation from here. And we can say that this is going to be equal to 1,200 meters divided by 1.60 meters per second, multiplied by cosine of negative 24.9 degrees. This is equaling 826.86 seconds. And we can say that L would then be equal to the velocity of the boat relative to the water times sine of phi plus the velocity of the water relative to the shore times t sub w. This would be equal to 1.60 meters per second multiplied by sine of negative 24.9 degrees. Again, plus the current, essentially the speed of the current, 0.80 meters per second, close parentheses, times 826.86 seconds. This is going to equal 104.47 meters. And finally, T sub R would then be equal to L over V sub R. This would equal 104.47 meters divided by 3.0 meters per second. That's how fast he can run. This would equal 34.82 seconds. And we can find the total time to be equal to 826.86 seconds plus 34.82 seconds. This is equaling approximately 862 seconds. So to summarize, we must point the boat 24.9 degrees upstream, taking 827 seconds to cross, landing 104 meters away from the point directly across from his starting point. So 104 meters from start. And then we can say he runs the 104 meters from the landing point to the point directly across the starting point in 35 seconds. So he runs for 35 seconds, giving a total time of approximately 862 seconds. In minutes, this would be approximately 14.4 minutes. That's the end of the solution. Thank you for watching.